So now we're going to make a short little video that will go with a homework sheet that you have, okay? And it's about making graphs. Now, what was the actual velocity of that little red car from our lab? What was it? 5.6 tiles per second. Okay, so our little red car had a velocity of 5.6 tiles per second. Okay, and let me show you a couple different ways we could graph that. All right, one, we could say, okay, here's a graph of velocity, and the y stands for velocity, and the x stands for time. Who's missing on this graph? Distance, right? Now, if we wanted to graph on a little graph like this, the velocity of that car, above 0 is positive and below 0 is negative. So we could say 1, 2, 3, 4, 5, 6. And then up here, 5.6 up here to make a little dash. And just make a straight line like this. And that is a graph of the velocity of the car. And then as time goes by, doesn't the car just keep going the exact same speed? Does that make sense? Now you're not used to seeing graphs like this. All right? But if you look at this graph, this car has a positive velocity of 1, 2, 3, 4, 5.6 meters per second as the seconds go by. Right? Okay, cool. Now let me show you another way we could graph this. This is what you're used to seeing. What if we've got time down here, except for now on the y, we're going to put x, or distance. Does that make sense? Now, we can make this graph easily. How far did the car go in our first experiment? How many tiles down the track did we measure? 10. So if we were going to graph the first little experiment, we were testing the red car, we could say the car went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tiles. So this is the distance in tiles. And then it took 1, 2, 3, 4.5 seconds. So we could go up here, 4.5 and 10. And boom, we could put a dot right there. And that is the one measurement that we took for the car. Right? Now let's backwards regress to 0, because when it crossed the start line, it had gone 0 tiles and 0 time had gone by. Now, if I connect the two dots that I know, and I also understand that this is an electric car going the same velocity the whole time, then I could do this, and that should look very much like something you're used to seeing from Algebra 1. That's just a regular old slope line graph. Does that make sense? So we can talk about this now like we're in algebra class. We've just made an algebraic graph of this, right? And there's a bunch of cool stuff in this graph that you might not realize, okay? But notice we have the distance. The distance is 10 tiles. And we have the time, 4.5 seconds. So we know that the velocity is 10 tiles in 4.5 seconds. So the velocity of the car we calculated to be 4.5 tiles. That's not right. 10 tiles in, it was 2.2 seconds, right? Sorry, people at home. The original time, I was wrong, was 2.2 seconds. So that gave us 4.5 tiles per second. All right, now I'm done messed up. I've done messed up. I wish you little weasels would have stopped me. Somehow it's your fault and not mine. 1, 2. So yes, when we did it originally, the original time that had gone by for the car to drive 10 tiles was 2.2 seconds. My bad. So we went 10 tiles in 2.2 seconds for a velocity of 4.5 tiles per second, right? Where can you see on this graph 4.5 tiles per second? Anybody at home? Where can you see the 4.5 tiles per second on this graph? All right, let me tell you. 4.5 tiles per second, that's the slope of the line. So the velocity is the slope of the line. Let's look at this old-fashioned formula you should be used to seeing. Y is equal to mx plus b. What do you think about that? Does that make sense? Y is equal to mx plus b. Okay, now b is the y-intercept, so b here is 0. Does everybody agree with that? Okay. Y is your final distance on the y. So you go up here, that's 10. M will be the slope of the line, right? And I'm telling you that the slope of the line is really the velocity. And x is the amount of time that went by, because this is the x-axis, 2.2. So if I take the plus b off, because the y-intercept is 0, then you'll see very simply that this y is equal to mx. This is v is equal to d over t. If you don't see where I'm coming from, how can I get this v by itself? Now, isn't that distance divided by time? So we can always apply the line formula, the slope line formula from Algebra 1 to any constant velocity. And now we can make things work together very easily, right? So what if we tried this? What if we tried this? What if we said, hey, I've got another car that I'm going to race. I've got another car that I'm going to race. But it's faster. And I'm not going to let it start until a second later. How do you think that would look on our little graph? If it didn't start until 1 second later, then its line would generate from right here. That's where its line would spawn from. Does that make sense? And then if that car was faster, how would that be represented in the line slope? If the velocity is the slope of the line, and this car had a higher velocity. Samina? That's right. Then you're going to have a higher, steeper slope to your line. So if you saw this, right? And then what will happen right here on the graph? What would that mean? If this is the original car, and this is the faster car starting 1 second later, what is this space on the graph? Yeah, where he passed them or caught up with them or hit them, right? If they're on train tracks, this will be a collision, right? Or this is where they passed them if there were two cars. Does that make sense to you? All right, cool. That's just a little quick glimpse into some stuff you're going to be seeing.